Okay, so in this video, we'll try to show um, a couple properties for metric spaces. So let's call this problem one. The sequence space, so R to the N. So this is the set of all infinite sequence, so sequence space. Of yeah, the set of all infinite sequences. And these sequences, they may be bounded or unbounded. That doesn't matter. So I'm going to define this function. Um, so let's say x. So the elements of this space is of course sequence. So you can think of it as x1, x2, and so on. Y is this sequence, y1, y2, and so on. So I'm going to define the distance or some function between two sequences to be, first, I'm going to subtract their corresponding entries. Then I'm going to divide this by 1 plus that number. Then I'm going to multiply this by 1 over 2 to the power of I. And I'm going to sum this from I goes from 1 to infinity. Okay, so the question, or what we want to show is that this is a metric space. So to show this is a metric space, so I just need to verify those four properties of a metric. The first thing that we may want to check, however, notice that this metric is given in terms of infinite sum or series. So it will only make sense if this series converges. Because what if this series doesn't converge? Then what's the value for the metric? The metric has to give you a value, right? Um, so we need to check whether or not this metric always gives us a value. So I could say for the proof, first we show that this metric is well defined. In other words, does it always give you a number? Okay. So how to show this? So since x to the n minus y to the n, so this number is always less than or equal, it's always non-negative, right? Because it's the modulus. This is always less than or equal to 1 plus that number. Okay, I just add 1. So both of these numbers on the left and the right of the inequality, they are both non-negative, right? So the number on the right, this number here, is never 0. In fact, this number is strictly positive. So let me divide through by it. Okay. So of course this holds for all natural numbers then. So divide through by that. So 1 plus. And if you divide through, you just get 1 over there. And let me multiply both sides by, let me just multiply both sides by 1 over 2 to the n. Okay, of course, that does not change the inequality sign because this is non-negative. So again, this holds for all natural numbers. And now we just need to remember something. So I think it's called comparison test. Um, so, uh, so recall comparison test. So that says let AN and BN be uh, sequences of real numbers, or sorry, of non-negative real numbers, I think it was. So non-negative real numbers such that the A's are dominated by the B's. So it says if the B's converge, so if this series now is convergent, so we write it as sum less than infinity, then the A's also converge. Okay, so this is known as comparison test. So if you look at what we have here, this is your B's, right? And these terms are your A's. And you could show, although you don't need to show it, but you could show since the summation from n goes from 1 to infinity of 1 over 2 to the n converges. So this series is finite, right? It follows that. So these guys converge, therefore this one is going to converge. But what is that? That is just the metric. That's just the metric that we defined earlier. If I sum over here, that is just this metric. Okay, and again, doesn't matter if you use I or N, same thing. It's a dummy index. So it follows that this one, so 1 over 2 to the n, what was it? It was x to the n minus y to the n all over 1 plus that. Also converges. Okay, and of course this is just the metric. So the metric is well defined, right? So whatever um, sequence x and y we throw into it, it will always give us a number because the series that is being used to calculate this metric value will always converge. It will always give us a number. So the metric is well defined. So now we need to show that it satisfies all those properties of a metric. So M1, is it non-negative? So since xn minus yn, the modulus of it is non-negative. And so the numerator, I'm looking at these terms now. So the numerator and denominator are non-negative. So 2 to the n into 1 plus this term. It follows that t of x comma y is always bigger than or equal to 0. Okay, because the numbers that we're going to be summing in this series, they are non-negative. So if the series converges, it's going to converge to a non-negative number. Therefore, the metric is non-negative. Let's get a new picture. M2. Actually, let me take the metric. So use it. Okay, so just to keep in mind what the metric is, I'm just going to have it over here. So we could keep in mind that this is the metric. Okay, so M2. M2 is, so that's coincidence. So if you take d of xy happens to be 0, um, then this means that this series is summing to 0. Okay? Then that means that series is summing to 0. And of course, we know now that all those terms that are being summed in this series are non-negative. Okay, so if you're summing all these terms in your series and it's non-negative, then that means that each one of these terms, each one of these individual terms have to be 0. Because if the answer is 0, so each one of these guys must then be 0. Okay, and this is true for all I. So each one of those terms must be 0. Okay, if each one of those terms is 0, so just solve that equation. So if you multiply through by the denominator, then that's the same thing as saying xi minus yi is equal to 0 for all I in n. And of course, since this is the modulus, we then immediately know that xi equal yi for all terms. Okay, so therefore, the sequence x is the same as the sequence y. So we have coincidence. So for M3 now, okay, so symmetry is obvious. Uh, okay, it's obvious since right, so symmetry is obvious. And M4, so the triangle properties. So let's see how to do this one. So xy, see summation, I goes from 1 to infinity. Uh, 1 over 2 to the I xi minus yi all over 1 plus xi minus yi. Okay, so again, the trick is we need to add and subtract zi. So z will be another sequence. And again, these sequences could be unbounded. It doesn't matter. Xi, so subtract zi, then I add zi minus y minus yi, and so I need to do the same thing below as well. Xi minus zi plus zi minus yi. So I need some way to pull this thing apart. Um, okay, let's do this one first. So of course we know that um, we have triangle inequality for this one. So if I sum over here, that's less than equal to this sum plus this sum. Okay, so what I'm saying is that this is less than equal to the summation of I goes from 1 to infinity. So this term I'm taking as A and this term I'm taking as B. So we'll handle the denominator in a bit. Let's just focus on the numerator. So it's 1 over 2 to the I, xi minus zi, and below, so that's my first term, plus second term. So the next one is zi minus yi all over 1 plus xi minus zi plus zi minus yi. Okay, so if I look at this term here, it's x and z, but in the denominator I have stuff with y. So I need to get rid of that stuff with y. Okay, so let me see what it is. Um, so you just need to think back to fractions. So if you have two fractions, p over q, um, and p over q plus 1, which one? So forget about some of them being negative. Let's just say p and q are always positive. Which one is the bigger fraction? So the bigger fraction is this one. The bigger fraction has a smaller denominator. Okay, so that's all we need. The bigger fraction is the one with the smaller denominator. So actually, I could bound this term. I could bound this term by something if, so I'll bound it by something bigger if I could throw away things from that denominator. Okay, so the technical way to write all of that is this one. Um, so we can write it like a plus b divided by 1 plus a plus b. Okay, so this fraction is less than or equal. Actually, I just need a on top. Actually, I just need c on top. Let's call this c. Okay. So this fraction is less than or equal, so I just make the denominator smaller. Because if the denominator is smaller, um, then the fraction is bigger. So how would I make this denominator smaller? Well, I just remove one of those terms. So I just remove the a from it. Okay, so we have that bound there. Um, so now let's go back to what I have up there. So that basically means I could throw away some of those terms in the denominator. What do I got up here? This is xi minus zi. So the terms with the y, I want to throw those out. So I keep the terms with the x and the z. So I could keep right, and the zi minus yi, I could throw that, out. Or actually, uh, you could get that using triangle inequality. Yeah, plus the summation from I goes from 1 to infinity. So you could You actually don't need this. You could go from here to here if you use triangle inequality on the denominator. Okay, but since I already have that, we'll work with it. 1 over 2 to the I. So I have z and a y. So I throw away everything in the denominator that doesn't have, that has an x in it. So I'll keep the zi, I'll keep the yi. 1 plus that. Okay, of course, I pulled out what I have in the denominator is the negative of it, but of course, you could pull the minus sign out. And this thing, so that's just equal to d of xc plus d of zy. So that's triangle inequality. So therefore, the sequence space is a metric space. Okay. Okay, so the next example we want to look at is something to do with a pseudometric. So what is a pseudometric? So suppose X is some non-empty set. Let's define a function. So a pseudometric is, you can think of it like a almost metric. Okay. This could go into R. It doesn't have to be that, but let's just keep it as that. So this thing, actually, let's put it in R. So this thing, so rho goes from X cross X into R is called a pseudometric if it satisfies the following properties. So I don't want to use M1. Let's just call it property 1, 2, 3, and 4. So the first property, for any x, y, z in this set, I have this. So the first one is x comma y is non-negative. Okay, so this is the same thing as M1 for the metric. The second property, actually what might be good, let me write out the 4 properties of a metric. Okay, so I'm just going to quickly list out the 4 properties for a metric. So the next one is rho xy equals 0 if and only if x equal to y. The third property is rho of x comma y equal rho of y comma x. And of course, the fourth property is triangle inequality, rho of x comma y less than equal to rho of x comma z plus rho of z comma y. So this is for metric. A pseudometric is when you have some problem occurring here. So this is no longer if and only if a pseudometric. You get this way, but you don't get the other way. So that is for a pseudometric. Rho of x comma y can be 0, does not, if rho of xy equals 0, This does not necessarily imply that x equal to y. Okay, so if x equal to y, the pseudometric will tell you the distance between those points are zero. But there will be points, so for pseudometric, what might happen is you put in two different points and the pseudometric is giving you zero. So to the pseudometric, it's like, okay, these two appear to be the same points, but you of course know they are two different points. And why that's interesting is because we've already looked at a space that might be or a metric on a space or metric that might have been a pseudometric if we did not define the space properly. So um, what I mean by that is what I mean right now. So it's given by this example. So let fancy R A B be the set of all real valued. Real value just means that these functions will give you a real number. So real valued, the fancy ideas means that you could integrate them using the Riemann integral. So be the set of all real valued Riemann integrable function. Riemann integrable. On closed interval AB. Okay, so these are just the functions you could integrate using the regular integral that you all did in undergrad. So for the space now, if I take 2 points in the space, so of course, when I say points, I mean functions, because if it's points, so for x and y belonging to this space, then that means that x and y are Riemann integrable functions. So x and y are actually functions. But for 2 points in the space, we're going to define, uh, let's use D. So we'll stick to D. D of xy to be, we're going to take the module, so we're going to subtract them, take the modulus of that, then integrate it from A to B. And now this thing here might look familiar because this thing is just the D1 metric from the notes or the L1 norm. Okay, so it appears that this thing should be a metric because, well, that's what we learned so far. The problem is that it is a metric on the space of continuous functions. We change the space. The space is now Riemann integrable functions. So we want to show that this, well, I can't say metric anymore. This function is a pseudometric. And not a metric. Okay, so to show it's a pseudometric, we need to just verify these four properties. So the first, the third, and the fourth property, the showing that for this function, we've already looked at that. That's the same as the proof for it being a metric. So all we pretty much have to do is show that the second property doesn't work. Okay, so you could try to do properties, okay, right here. Properties 1, 3 and 4 um, follow from D being a metric on the set of continuous functions between A and D. Okay, so the proof of that is the same. The problem is the third one. So in order to show that D is a pseudometric, I have to show this. I have to come up with 2 points, 2 functions that are different, such that when I plug those 2 functions into that function D, it gives me 0. And there are many functions that will do this. An easy example. So once you see the example, then you'll see the basic idea how to get these functions. The thing is, once we remove the restriction that the functions need to be continuous, we are allowed to choose functions with discontinuity. And the easiest type of discontinuity is one removable discontinuity. So let's define 2 functions. So these functions will be discontinuous functions at one point. Okay, there are many, many examples you could think of. These are just easy examples. So consider the 2 functions in this set. The first function, let's call him x of t, and I'm going to give it a value of 0. So let's just say, for example, so this is on AB. Let's just take, for example, AB is equal to 1, 0. Okay, but it will work for anyone. So 0, 1. So between 0 and 1, and the value at 0, I'm going to say it's 2. And y of t is similar, except I'm going to put that as 1. Oh, so I can't use x. I can't use x there. Yeah, so let me change the name of the function then, right? I need to change the name. So let's use f and g, because I'm already using x as the x coordinate. Or I can use t. Yeah, I can use t. X, y, yeah, and I use t. There we go, t. So this t is 0 and then 0 between t. Right. Okay, so what does these functions look like? Do a little sketch. So here's your t-axis. So they are both 0 uh, for almost all the points. There's 0, except so here's 2 and here's 1. So x of t takes its value up here, and y of t takes the value down here. Okay, so there's obviously these are 2 different functions. So let's plug these 2 functions into this metric and see what we get. Well, it's not a metric. Into this function, into D, and see what we get. So so let's just work out what is x of t minus y of t. Okay, so subtract x from y. So at t equals 0, it will be 2 minus 1, which is 1. 1 at t equal to 0. And for t not equal to 0, it will just be 0. 0 minus 0. 0. So 0 less than t less than equal. Okay, so therefore d of x comma y is equal to the Riemann integral from 0 to 1. So again, it doesn't have to be from 0 to 1. You could do from a to b. But A to B, 0 to 1, it's pretty much the same thing because you could always extend AB for any AB to the interval 0, 1. Okay, so from 0 to 1 of the modulus of the difference dt. So from 0 to 1, um, well, actually, we could just write what this answer is. So this answer is just going to be 0, right? Why is it going to be 0? If you had to integrate this function, so let's move the point away from that axis. So let's say here's 1, here's 0, and here's 2, and here's um yeah, let's just say here's 1. Um, yeah. So let's say this is your function, and at the value of 1, it jumps to 1. So you would have proven in undergrad that the Riemann integral could integrate these stuff. So it could integrate functions with finitely many points of discontinuity. So jump discontinuities, which is this one, and this is removable discontinuities and finitely many jump discontinuities. The Riemann integral could integrate it. And for this one, it somehow doesn't care about what the function is doing at individual points. So that's the blessing and the curse of the Riemann integral for when we use it to define metrics and even norms, because this problem will happen if you use it to construct a norm on this space. It wouldn't be a norm. It will be something that is almost a norm. It will fail for the same reason. It will be called a pseudo norm. So the problem is that to the Riemann integral, functions like this and functions that are zero for all points, the Riemann integral cannot tell those functions apart. Okay, so that's what's happening. And if we want to construct, for example, a metric space, we need to be able to tell those things apart. So therefore, since x and y are clearly different functions, but when I throw those two functions, which are different, into this d function, I get it to be 0. So therefore, d is a pseudometric. Okay, so d is a pseudometric, and let me put this space. D is a pseudometric on the space of all Riemann integrable functions from a to b. Oh, so now, so I'll just do a little bit here so we see what's going on. So this is the this is a space of all functions. Any real valued function you could think of, that is a space. Right? So this is a space of all real valued function. Any function that give whatever you throw in, it gives you a real number. The continuous functions, so that we say pick some set. So pick some subset of the real numbers. Close interval a, b. The continuous functions, they live here. These are the continuous functions on that closed interval AB. So all continuous functions are Riemann integrable. So the Riemann integrable functions, those guys live here. Okay, so we have expanded the space. So that pseudometric, if we define that same function on the space of continuous functions, it is a metric space. But when we try to expand it to get all the Riemann integrable functions, it fails. So it becomes a pseudometric. Now the question is, could you fix that? And the answer is yes. We could actually fix a pseudometric because it's so close. It's just one condition that's causing us some problem. The metric can't distinguish between points that are very close together. The metric should be able to distinguish between them, but the metric is telling us it's zero. So it's telling us that these points are the same. There's a way around it, using equivalence classes, but I'm not going to do that problem. So you might, if you want to, you can look that up. Basically, you just have to form an equivalence relation on that space, and all those problem points, it will group those problem points together. So we say, let's say this set, these are all the points that the integral essentially can't distinguish between. And you construct a new space where this will be essentially mapped to zero, which is a quotient space. Okay, but you don't need to know that. So just know there's a way around it. You could convert pseudometric into metric. Okay.